Thank you. So today I'm going to be telling you about an era that has been at least alluded to several times already, so you know something about, but I'm going to try to approach it in some detail. And that's this era we call the cosmic dawn, which refers to the formation of the first luminous objects in the universe, stars, black holes, and galaxies. I'll start off by trying to convince you, perhaps for the second time, about why you should care about this time. And then I'll go into what we've done so far, which is where the first part of the computation comes in. And the second is what we're going to be doing in the next 10 years, we hope, which also includes computation. OK, so here is my slide summarizing the history of the universe, with the Big Bang at the left over here, and then we're at the right 13.7 billion years later. I describe myself as a cosmologist. I'm a theorist. Cosmology means different things to different people. So to Kim, for example, it means understanding the history of the universe and its overall contents. For some of us who are more astrophysically oriented, it means understanding the history of structure within the universe. And so that's the direction that I'm going to be focusing on today. Where do galaxies come from, much like Elliot talked about this morning? Right, so in that context, we want to really understand the sequence of events that led to the present day. And over the past 50 years, really, we've made a lot of progress in that. We understand the earliest phase that we can study the cosmic microwave background very well, and you've talked about that several times. People who study this cosmic microwave background are fond of referring to it as a baby picture of the universe, because that's the earliest view we can get of the universe, at least with photons. And that's true if you are the kind of cosmologist who thinks about the universe as a whole. But from my perspective, and I'm interested in the objects inside that universe, those aren't around at that time. Instead, the cosmic microwave background is basically setting the initial conditions from which everything will grow. And so I think of it more as a picture of the DNA of the universe, of what the sequences that set up the structures that will later form. Okay? So we know that very well. We also know what the universe looks like around us today very well, and you've heard about that. The fundamental point is that interesting objects, almost all of them, are organized inside of galaxies or are collections of galaxies. Those galaxies are fairly large. They are orderly, or at least have an orderly form of disorder. They are not growing very rapidly. They are not interacting with their neighbors very much. And so those are basically mature galaxies. Over the past 20 years, there's been a huge effort at pushing our understanding of galaxies to earlier times. And so by today, the most distant galaxies we see them as they were about 1 billion years after the Big Bang. So that's 13 billion years of history that we can observe. But it turns out that the galaxies that we see are very recognizable analogs of the ones in the present day universe. Okay, they have important differences. They are smaller. They are growing more rapidly. They are interacting more violently with their neighbors. They have less structure to them. Okay, but fundamentally, they're made of the same kind of stars and gas that we see around us today. And so I think of these observations as showing us what galaxies were like in their teenage years. All right, a little bit more dramatic than as adults, but fundamentally, they look the same. That's as far as we've gone so far, okay, about 1 billion years after the Big Bang. And so the era that we're missing is what we call this cosmic dawn, the era when the first galaxies formed. And in human development terms, I would say the childhood of the first galaxies as well, going up to the sort of recognizable things that we see around us today. Okay, so that's the big reason why this cosmic dawn is so interesting. If you want to see baby pictures of the universe, the things that are in the universe, this cosmic dawn is where we want to look. Right, there are some bigger questions hanging around that. The first is that when that first star forms is a truly transformative moment in the history of the universe, because before that moment, the universe was very, very simple. It was described by a handful of numbers, the matter density of the universe, the expansion rate. That's about it. Okay, I mean, those kinds of things, and you can list those numbers on 2 hands. And very simple physics, gravity and fluid dynamics and a little bit of thermodynamics. Okay, once that first star forms, things get very, very complicated essentially instantaneously. Once you have all that energy around from fusion, all sorts of very complex physics start to matter very quickly. Right, so this is a visualization of a simulation that I think was ultimately due to Mike Norman's group. These are the people who did the visualization of the site of one of the first star formation things. Right? So this birth of complexity is from a philosophical standpoint, very important. The second key point that you, I think, have heard about somewhat already is that these first stars may have been very exotic things. Okay? In those teenage galaxies, stars look more or less like they do today. These very first stars may have been very different, and certainly they formed through a different mechanism. That different mechanism is that in present-day environments, a lot of the radiative cooling that Mark mentioned this morning happens because of heavy elements, oxygen, carbon, CO, right? Those kind of things. Those weren't around when the first stars formed because they were not formed during the Big Bang. However, those first stars would have produced them. Okay? And so the first stars were this very brief phase that carried the seeds of their own destruction. Quite literally, they could not have formed at later times. This is another simulation that shows the dispersal of these heavy elements as part of this transformation. The blue blobs here are basically the little bubbles growing around the exploding stars that are carrying those elements around. So there's this very exotic phase of star formation that we haven't yet seen, but we would like to understand. All right, the next key point I want to go into in a little bit of detail. So the cosmic microwave background, the reason it's sort of a snapshot of the universe 400,000 years after the Big Bang is because that was a phase transition in the chemistry of the universe. Okay, so before that point, the universe was hot enough that if you had a proton and an electron, they would be separate. You'd have an ionized atom. All right. Once you reach about this time when this cosmic microwave background last scattered, that corresponds to recombination. Right? The electrons and the protons get together into atoms. They stick that way because the photons that are left over just pass right through those atoms. They aren't energetic enough to ionize them, and so they just pass right on by until they hit our telescope. And so from 400,000 years after the Big Bang onwards, the universe is neutral to 99.9% basically. However, once you form the first luminous objects, that can change because these stars now produce photons with high enough energies to ionize the atoms. Okay? And we call that process reionization because at the very, very early history of the universe, it was ionized, then it went neutral, then it got reionized. Right? And I'll be talking about this reionization transition quite a bit today. Here's a visualization of it. What you're seeing are the first galaxies are forming. They're producing stars. Those stars produce these high-energy photons. Some of them leak out into the universe around them and build little ionized bubbles. And that's the blue blobs that you see growing here and here. As you get more galaxies and the galaxies get bigger, you get more and more of those ionizing photons leaking out. And pretty soon you're going to see this whole box of the universe go to basically be transparent. Right? And so this reionization event is sort of the hallmark consequence of the first stars. And we know that from the point when this reionization occurs, the universe, at least outside of galaxies, remains highly ionized to the present day. Today, it's ionized like 99.999%. Right? This has very important consequences not only for this just a general picture of what's going on in the universe, but also for subsequent generations of galaxies, because it's this material in between the first galaxies that is the fuel for later generations of galaxy formation. So if you want to understand how gas is incorporated into galaxies, you need to understand these feedback processes. And they are strongest during this earliest phase of the cosmic dawn. And finally, Elliot talked about black holes this morning, and he mentioned that they form early on. So this is also the era when the first black holes form, not just the first stars. I won't have a lot to say about black holes specifically, but they're sort of underlying a lot of things. Elliot made the point that these things affect galaxy formation, and this simulation is illustrating that. And those same kinds of questions hold during the cosmic dawn. I should say this simulation has nothing to do with the cosmic dawn. It's just the best picture I could show of galaxies, of black holes affecting galaxies. All right, so that is why you should care about the cosmic dawn. Now I want to talk about what we know. And what we know is all from theory. So keep this in mind, as everything I tell you is most certainly wrong. All right, so the goal, what we want to do, is get a detailed picture of galaxy formation during this early era. And that's really hard, okay? Because what you need to do is you need to take what Elliot talked about this morning, and then you need to put what Mark talked about this morning in, and you need to add a bunch of other physics that we haven't gone over because it's another level. And this flowchart very crudely illustrates the kinds of things that you want to talk about, right? So what the star formation part is right inside of this circle here, okay? And that's extremely hard in and of its own. You want to do this for a galaxy, and then you want to put it in one of your big boxes and watch how these galaxies interact with each other. Okay? So this problem is much too hard for us to answer right now. So we break it down into pieces, and I'm going to talk about a couple of very different methods for approaching understanding how these galaxies form, and try to give you some context for what we're actually doing as theorists. All right, so the first is computational astrophysics. And the goal of this, in this context at least, is to make precise numerical calculations from first principles of very specific parts of the problem. Okay? And the classic one is to try to build the first stars. And the reason this is kind of a classic problem is because it's something that, at least in our heads, we can imagine doing right. Right? This is one era where the physics is actually not that bad. And that's because, as I mentioned earlier, at the time of the cosmic microwave background that's setting the stage for everything, the universe is defined by just a few simple numbers: the matter density, the expansion rate, et cetera. And the physics that you have to incorporate before that first star forms is straightforward. It's gravity, it's thermodynamics, and it's fluid mechanics. Okay? Now, at the time of the cosmic microwave background, that physics is actually very simple. Right? The reason that you don't have a talk about the CMB here is because you don't need computers to understand the CMB. The physics is straightforward. Once you get to start to approaching forming these first stars, it gets complicated. You need computers to solve the equations now. But it's the same physics. It's physics that we fundamentally understand. All right, so its formation is a well-posed problem, and you can go after that with a computer and expect to get something like the right answer. So I'm not going to say a whole lot about simulating the first stars, because I know Mike talked about it some yesterday. I want to just basically tell you the overall picture that has emerged from these simulations. This is the same visualization from Mike's group that I showed earlier. So stars, we know that the first stars will form in small dark matter clumps, maybe 100,000 times more massive than the sun. That's over 1 million times smaller than the Milky Way. What happens is that as the gas falls onto that clump, it gets heated up from basically it collides with itself and gets heated up. So in order to form a star, to get to higher densities than that, you need to cool the gas. You need to get rid of that heat. Normally, that would happen through radiation from heavy elements. This first star, there is no heavy element. That makes the problem easy. And all you have to worry about is the stuff produced in the Big Bang. And it turns out that the thing the thing by which you cool is molecular hydrogen. Okay, so you just have to trace some very simple chemical reactions. Well, I say simple. There are 37 of them or something, but computers can solve 37 equations at once. It's not that bad. Once that cooling occurs, you're left with a gas clump that has a mass several times larger than that of the sun, or several hundred times larger. Okay, that's kind of where the simulations get really hard. Okay, and we sort of have to stop them for computational reasons. We know that if that clump is left alone, let me say, as of the first simulations that came out, okay, they suggested that if that clump were left alone, it would just contract and basically form one big blob that would form a very massive star. Not a ridiculously massive star. We're talking about a star that's maybe a couple hundred times as massive as the sun. And that's a kind of star that we can calculate its properties. But it would be much different than the one solar mass star that is typical of the Milky Way, as Mark showed this morning. Okay. So that was the picture as of the first simulations that did this. I think were published a decade ago, 2001 or 2002. And since then, we've been steadily improving computational power and looking more and more closely at this problem. And unfortunately, we've kind of gone backwards over that decade. If you asked a theorist who studied this era 5 years ago what the first stars looked like, they would have said a couple hundred times as massive as the sun. Now the answer is much less clear because we've actually looked at the problem a little harder. So the first challenge is that the simulations simply, even as big as computers are today, they still can't do the whole problem, right? And so you have to you get stuck somewhere, and then you have to kind of guess what happens after that. And recently, there have been a few lines of evidence that this picture of a star a couple hundred times more massive than the sun may be an overestimate. So the first is that the accretion onto this protostar actually will happen through a disk. And it turns out that at least in some simulations, those disks can fragment just because of the same way, basically, that Jupiter would form in our solar system, gravity. So this is one of those simulations. The first star forms in the center of this red blob right here. and you've got a disk around it that's spinning around and forming what looks like spirals. And about 100 years after that first star forms, which of course is extremely short time scale by astronomical standards, a second protostar appears to form in this simulation, and then you get more as time goes on. Okay, so rather than get a single very, very massive star, you might just get a few very massive stars, so tens of solar masses. There's also some chemical effects that may cause fragmentation, and the turbulence that Mark mentioned this morning is very hard to resolve in these simulations, and if you put it in, basically, which is done by hand right now, if you put enough of it in, then that could also cause fragmentation. Okay? So right now, we don't actually know the answer to how massive these stars are. They're likely to be at least many times more massive than the sun, but we don't know their exact properties. And what we need are bigger computers to basically hammer at this problem even harder. All right, the second challenge in doing these kind of first principles calculations is that your first principles had better, in fact, be correct. And recently, there's been an effect pointed out that illustrates how hard it can be to figure out what your initial conditions ought to be. And this actually connects to the baryon acoustic oscillations that Kim mentioned this morning that are one of the techniques for studying dark energy. So those happen basically because the gas in the universe is moving relative to the dark matter. And that happens since the time of the cosmic microwave background. And although the velocities when stars are forming are small, okay, they're nevertheless very significant compared to the typical velocities within the structures that form these very first stars, so kilometers per second. And so when you imagine that you have some dark matter clump that's forming and has some gravity and it's trying to accrete the gas around it, if the gas is sitting still, that's an easy process. If the gas is flowing by really fast, it gets very difficult for the gas to sit still long enough to fall in. Okay? So if you include this relative motion, it actually dramatically changes where the first stars would form. So on the right-hand side, this is a map in a particular calculation of where these first stars would have formed if you ignore this velocity effect. The red blobs are showing you where those would form. On the left-hand panel, you're seeing that same kind of map, but now including this relative velocity effect. And it's a pretty dramatic change. It's not a subtle thing. All right? And also, the numbers down here, these are distances across the size of this little box. And these are in megaparsecs. Okay? So that's a parsec is about 3 light years. So this is about 1 billion light years across. Right? And the structures, the locations where these first stars are forming are changing on sort of 100 megaparsec or 300 million light year scales, right? Because of this fairly subtle effect that nobody had really noticed until about 2 years ago. Some guys at Caltech had pointed it out. All right, and then the last challenge is that as I mentioned, after the first star forms, things get very complex very, very quickly. And although the formation of the first star is a well-posed problem that you can attack with computational astrophysics, everything after that, basically, you have to pick and choose very carefully. Okay, so what I'm going to do now is step you through kind of a cartoon picture of how we could go from the first star to what we might refer to as the first galaxy, meaning the first structure that can form stars over long, sustained timescales. Right? The picture that I'm going to describe is very, very crude. It's one of these things that's definitely wrong, but it will at least illustrate some of the complexity in doing this. Okay, so the first stars form here. They produce, once they form, right, they're producing a lot of this high energy radiation, and they're blowing up fairly soon as supernovae. Right? All of that radiation in supernovae can actually blow out the gas that's in the same little dark matter clump and basically shut off any further star formation in that same little clump. Okay, so you form a little clump of stars maybe, and then it destroys everything else. Right? But that's those same effects, the radiation and the supernovae, as they go by nearby dark matter clumps, they're going a little bit slower out there, they may actually trigger star formation out in those nearby clumps. Okay? But because the supernovae have carried around the heavy elements produced in the first stars, the character of star formation in these nearby clumps may differ from that in the first one. Right? At the same time, on even larger scales, the radiation background produced by these first stars will actually destroy the molecular hydrogen in the universe. And remember, you need that molecular hydrogen to form subsequent, to form stars, to cool off the thermal energy that you start with. And so as this radiation background builds up from the stars, it starts shutting down farther star formation unless you have enough of the molecular hydrogen in a single clump to block the center, right, from the radiation field. And the higher the radiation background, the bigger of the shielding gas that you need. And so the size of the clumps that can form stars is going to get ever higher as time goes on. Right? And eventually, you're going to start this reionization process. So one of the consequences of reionization is reheating. You heat the gas by about a factor of at least 10, maybe as much as 1,000. And that makes the gas harder to fall into the dark matter clumps as well. And so you farther shift up the mass scale of the clump that can form stars. Okay, so that's where you would finally get to a point where you could sustain star formation over large timescales, and so you might have a galaxy. But there are a number of steps in between here, and I've left some processes like X-rays out that will affect this as well. Okay, so there's a lot that you have to worry about. And if you're spending a week doing a calculation and you need to guess exactly what parameters to put in for each of these different unknown things, then it's very likely you're going to guess wrong in some way. And so your simulation is not going to actually reflect reality. So this is the key difference from simulations of galaxy formation that Elliot talked about that are appropriate for the later times in the universe's history. Because these external inputs, these radiation fields, the feedback from supernovae, from other galaxies and stuff, are not important. First of all, they don't change across the universe. They're nearly uniform at any one time. They don't change much in time. They're slowly evolving. And we can measure their properties. So you can just put them into your simulation and know that you're going to get the right answer in the end. At early times, though, the feedback processes generated by these large-scale effects are basically half of the interesting physics of galaxy formation, and they're completely unknown. Okay, so this is a picture of what's called the IRIS simulation of the Milky Way, a very recent detailed simulation of a galaxy like the Milky Way. You can do this and be confident that you're going to get something that looks like the Milky Way because you don't have to worry about these inputs. Doing the same kind of thing for a first galaxy doesn't really make sense because you need to guess so many things that are going in. All right, so numerical simulations have played a very important role in understanding this cosmic dawn, but basically they've done so by picking and choosing the problems they're going to attack very carefully. So things like forming the first star, that's a well-posed problem. You can also say the first star is there. Its environment is relatively simple because it's the first star, so then you can explode it and see what it does to its surroundings. And similarly for the radiation. All right, but we don't yet have the physics and the astronomical understanding to go from these first stars all the way to the first galaxies. So the contrasting approach is one that basically, instead of trying to build everything from first principles, tries to ignore as many of the first principles as you possibly can get away with and see what's left and see if that's interesting. Okay, so basically you ignore all of the hard part about galaxies. You say a galaxy is a blob that takes gas from the universe and churns it into stars. And then those stars will do some certain things. Okay, but you're just going to say, I'm going to assume that that happens with some efficiency. Okay, and I'm not going to worry exactly what causes that efficiency. It's just some number. Right? And then I'm going to look at the results of this model and see if I can identify robust aspects of what's left. Right? And if you can, and if you can relate that to observables, then you can say, all right, observers, go out and look at X. And if X gives you 0.1, then that's the physics that you're probing. If X gives you 0.5, then you're probing something different. Right? And so this is actually the side of the problem that I come from. I don't do big high-end computer simulations. All right? I work on trying to identify the big picture parts of the problem, although you'll see in a minute that that connects back to the computation. All right, so I want to give you an example of this, of a successful application of this approach. And it has to do with reionization. So this is a snapshot of a box of reionization. The white blobs here are the ionized bubbles that are growing and going to fill the universe. Right? And one of the things you could ask about this reionization process is what determines the morphology of these things, so shapes, how big they get, where they live in the universe, those kinds of things. I want to understand the pattern of the ionized bubbles. The simplification I'm going to make is I'm going to assume that we know basically where the galaxies live and at what efficiency they can produce the ionizing photons that we need. Right? And from that, I'm going to ask, okay, assuming that I know that, what are the interesting aspects of this morphology? Okay? And it turns out that calculating that morphology is something that's straightforward. Right? It's basically an exercise in counting. So I have some galaxy. I know how many ionizing photons it produces. All right? And I have around it a universe, and I know the density of that universe. So what I can do is I can compare the number of ionizing photons produced by the galaxy to the number of atoms inside of some volume. And I need one ionizing photon per atom to ionize it. Right? And so I can just figure out the volume of the universe that contains the right number of ionizing photons. So if I have my galaxy right here, I can just draw the ionized bubble around it, and I would be done. Now the challenge is that once basically the ionized bubbles are big, and these galaxies at early times are pretty close together. And so very likely you intercept a galaxy inside of your ionized bubble. And that one is also producing ionizing photons, so you can draw a bubble around it. But now you have a problem. The problem is that there's a region where both galaxies' bubbles overlap. And there you've used 2 ionizing photons per atom, and so you have some extras. And so you really want to spread those ionizing photons out around the edge there. Okay? And when you do that, first of all, that's hard because you need to figure out where to put those things. And you'll very likely intersect another galaxy and then another. And it turns out that during reionization, you probably have bubbles that are composed of thousands of galaxies all overlapping. Okay? So building from one outwards is very challenging. But it turns out that if you turn the problem around and you go from, instead of asking, start with one galaxy and build outward, if you start with something really big and you build inward, you can actually tackle this problem with what we call an analytic model. So that's something that you can more or less write down on pencil and paper, or at least do on a laptop or something. Okay, so from that, it turns out that you can produce basically the predictions for how big these ionized bubbles should be and around what kind of galaxies they should live. And you discover from that that this pattern of ionized bubbles is actually a very robust thing. You can change when this reionization event happens. Does it happen 200 million years after the Big Bang or 1 billion years? That will not in and of itself change what this pattern looks like. Instead, it's what kind of dark matter clumps do the galaxies live in that determines how this pattern will grow. Right? So now we can hand this to the observers and say, go measure this. All right? And then from that, I can tell you where the first galaxies lived. All right? So that's an example of this analytic approach. Okay? But often you want to make detailed predictions to hand to the observers. And so then you need to turn back to computation. Right? And so what I'm going to describe next is an implementation of this very simple, dumb photon counting approach with computers that gives you a nice, basically pretty pictures at the end. Okay? And we call this a semi-numeric approach because it's much more stupid than a full-scale numerical simulation about which you've been hearing, but it does a good job nonetheless. Okay? So what you do is you start with the same initial conditions that a normal numerical simulation of the universe would start with. So you have a box, and in it you put some little fluctuations in the density of matter inside the box, and those fluctuations are basically determined to match what you started out with from the cosmic microwave background, the initial conditions of structure formation. Now what you would do in a normal simulation is then you would turn on gravity, and gravity would calculate the gravitational force that each particle in the universe feels from each other particle in your box. And you would crunch those for a week on a supercomputer and see what kind of structures you form. Okay? In our approach, we don't do that. Instead, we use very simple physics, something called linear theory, which is basically saying that as long as the perturbations in the universe are small, you can describe them very simply. Basically, after a certain time, the amplitude of each perturbation just grows by the same amount. So you have your initial conditions for the box. If you want to evolve it by linear theory, you just multiply it by a single number, and you're done. Okay? That doesn't give you the detailed physics of galaxy formation. That's much more complicated. You have to do the complete calculation for that. But it turns out that from this linear theory picture, you can identify where the galaxies will form inside of this box. Right? So each of these blue spots is where a galaxy would form in our box. Okay? And we've calculated that not by following the gravitational evolution of the structure, right, but just by using this linear theory, very simple, and then using a trick from an analytic model to identify where the galaxies live. And then once you know where the galaxies live, you can use the trick to paint on the ionized bubbles and basically build the pattern, the morphology of the ionized bubbles from that, okay, in a box. Now the nice thing is that rather than take a week on a supercomputer, you can do this on a desktop. Okay? So this is what sits in my office. It's a really fancy desktop. You know, it's the nicest one you can order from Apple. But still, it's just a single desktop. It takes a few hours to do one of these calculations. Okay? So by basically figuring out what the robust parts of what the important parts of the calculation are using physics knowledge, you can vastly simplify the kind of computation that you have to do at the end. All right, and this pretty simulation of reionization that I showed you earlier, it's not actually a simulation. It's actually an even simpler version of what I just described. Okay, so this is a big box where they use this linear theory trick to basically paint on the ionized bubbles and watch how they're going to grow with time. All right, so we have these two approaches, basically one from first principles using a lot of computation and one from analytic arguments that tries to cheat as much as it can. Neither is entirely satisfactory. The computational part can only give you part of the story, and the analytic approach is basically brushing a lot of stuff under the rug. Okay? So what we need to do now is integrate these two approaches and better understand what's going on at this early time, okay, and sort of resolve the schism that's in our community. It's not quite as I don't know, cantankerous of a schism. Everybody understands that this is a problem, and we're all working together to do this. And we all understand that the way to go forward at this point is data. There are just so many unknowns out there that we need some actual numbers, some measure of reality to tell us where to go from here. So this is the Hubble Ultra Deep Field. This is the deepest picture so far taken of the universe. And hidden in here are hundreds of galaxies as they were less than 1 billion years after the Big Bang. And with that kind of information, we can now actually start to understand what's inside of these galaxies and start to narrow down the kind of physics that's important and do actual models of of early generations of galaxies at least. Okay, so it's the very beginning of trying to do that. Right? So my postdoc, I think, is one of the first people trying to do this with real quantitative models. And so that's one direction that you're going to see theory start to move in the next 10 years. But in terms of advancing the frontiers of knowledge, the more important direction is to actually get better observations. Okay? And fortunately, there are a lot of ways people are talking about doing this. I don't have time to talk about really any of these in detail, but I'm going to just focus on one, which is called the spin flip background. All right, so this is generated by a particular emission line of the hydrogen atom. So the hydrogen atom is a proton and an electron. They both are charges, and they both have this quantum mechanical property called spin. And that means that basically you can think of them as spinning electric charges, and that will give you a magnetic moment. And so you have two little magnets in the atom. If those magnets are aligned or anti-aligned, that's a slight energy difference. And that energy difference will produce a photon with a wavelength of 21 centimeters when it is emitted. All right, so 21 centimeters, that's like 7 inches or something. And that corresponds to a frequency of 1.4 gigahertz. So that's in the radio. This line was one of the first lines identified for use in radio astronomy, first predicted in 1945, I believe, and first measured in 1951. It was originally developed as a tool to map the structure of the Milky Way galaxy. Since then, it's been used extensively to study nearby galaxies. So these are maps of atomic gas in a lot of nearby galaxies. Okay? This spin flip line is extremely important in mapping the nearby universe. What we want to do is use it to map the very, very distant universe. And the basic reason for that is that, remember, after the cosmic microwave background scattered, the universe is neutral. And it remains neutral until this reionization event finishes, which we think is about 1 billion years after the Big Bang. So there's a lot of neutral hydrogen around to measure, to look for. So even though this is actually an extraordinarily weak transition, we can imagine doing it in the distant universe because there's simply so much hydrogen around. All right, so to describe the next part, I want to go back to the cosmological redshift that was mentioned a couple times this morning. The basic idea is that you can think of the universe, of a photon being emitted from some distant object and traveling toward you. It starts off with some wavelength, okay, and the wavelength determines the color of the light, and also whether it's radio or gamma ray or whatever. Okay, and that's a distance. And as this photon travels through the expanding universe, that distance gets expanded as well. And so if the photon starts out as an optical photon, it's going to get a longer and longer wavelength, which corresponds to more and more red light. So we call it the redshift. Okay, but that same process will happen to any photon as it travels through the universe. And so even these photons that begin at 21 centimeters in the radio, they will also redshift. They will get longer and longer wavelengths as they travel. Okay, and that has a really important consequence for using this as a tool. Okay, imagine that a photon begins at 21 centimeters right here and is emitted to an observer on the far wall. Okay, it starts at 21 centimeters. As it travels, it expands all that way, and say it ends up at 2 meters. Right, now imagine a photon that begins its life a little bit farther away. All right, it's also traveling and getting expanded as it goes. Okay, but it has more space through which to travel, or more time that it takes to travel, and so it has more expansion that will undergo. And so by the time it gets to the far wall, it will have a wavelength of maybe 2.1 meters. Right? So if you observe at 2.1 meters, you only see light that was emitted out here. If you observe at 2 meters, you see light that was emitted here. And so we can use the redshift as basically a proxy for distance. And by observing at different frequencies, you can see basically at the universe at different distances or times. And so what we can do with this single line is actually make movies of how the universe evolved over the entire period of the cosmic dawn. Right? And this is an example. This is one of these semi-numeric calculations. The colors is showing you the intensity of this particular spectral line. OK, so I want to basically try to explain to you how we're going to use this as a tool to measure astrophysical things. So this plot is showing what you would see if you measured the intensity of this particular line as a function of time over history. Okay, so instead of using time, I'm using the observed frequency, because remember that the wavelength that you end up with depends on the observed time. So the left-hand side is very early times in the history of the universe, and the right-hand side will be only fairly early times in the history of the universe. And then the y-axis here is, this is the intensity of the transition. We measure that in temperature units for reasons that aren't important. The 0 would mean that there's no signal whatsoever. If the signal is negative, that means that basically this particular transition is absorbing light from the cosmic microwave background instead of emitting it. And that would happen because the gas is cold. If it's a positive signal, that means the gas is hot and it's emitting light relative to the cosmic microwave background. All right, so here, this part that is shown right now, that's actually before the first stars form. It turns out that the gas is cold, and so you can see it in absorption. But that signal fades as you go to later times. Once the first stars in the history of the universe form, they flood the universe with this background radiation. And it turns out that this background radiation turns on this spin flip background again. Okay, it scatters through all of this neutral hydrogen and turns it on. And because the hydrogen is still cold, it turns it on in absorption. So we get a negative signal here. Okay. The black line that I'm trying to trace with my pointer is a best guess for how this signal would evolve. All right, all the other curves that you're seeing are very plausible variations around that curve. So there's a lot of variation that you can expect, and so by measuring this background, we would learn a lot about these stars. Shortly after the first stars form, the first black holes will form. They're important because they produce very high energy photons. Those high energy photons travel through the universe and they deposit some of their energy as heat. Okay, and so remember, we get absorption because the universe is cold. Once you start to heat the universe, that absorption turns into emission. And so the first black holes would be traced by a transition from cold to hot here. Right? And then somewhat later, at least by our best guess, this reionization process would occur when you ionize the gas, you strip the electrons and the protons apart, and so you destroy the spin flip background. And so the signal is going to fade over time as the universe is ionized. Right? And so one thing that we could try to do is just measure how this average signal is evolving with time by looking at different frequencies. Okay. Yes?
On that graph that you just kept showing there, is that a model or is that observed?
Oh, this is absolutely a model, yes. We've never seen this signal from a distant source. And I'll end by describing how we hope to shortly. Okay, so that is what you would see if you looked at the average signal across the whole sky, but of course there are structures that you want to observe, like these ionized bubbles growing. And this is another semi-numeric calculation showing what those structures would look like. So far, nothing has really been happening. Now the first stars are about to form, and you're going to see this whole thing turn blue. That's because they're turning the signal on. Now the black holes turn it red because they heat it up, and then these black blobs are the ionized bubbles growing during reionization. Okay, so we would want to map these structures to find out where the first stars form, where the first black holes form, etc. All right, to do that, we need to observe the photons. Okay, now remember, it starts at 21 centimeters, but it's going to be redshifted as it travels to us. And it's redshifted by a factor of 5 to, say, 30. And so that means that the wavelength of light that you end up with are going to be at least a meter across. Right? And this is going to be a very different regime from any kind of astronomy that you are likely to be familiar with, because the photons have a wavelength of a meter. And that means to observe them, you use something very simple that doesn't look like a telescope, it looks like an antenna. And that's not a coincidence. It turns out that the wavelength of light that, at least until very recently, we used to broadcast TV signals was about a meter. Okay? So a TV antenna is actually a telescope in the right ballpark to see this kind of signal. Unfortunately, that carries with it 3 very important challenges. The first is that if we're trying to observe at the same frequencies that TV transmitters are operating, the first thing we're going to see is TV, and we're not that interested in it. So if you took a spectrum of the sky in the frequencies we care about in Sydney, Australia, all right, this is what you see, and at no point in this spectrum can you actually do any astronomy. That's all terrestrial interference. So the usual answer for astronomers is to go away from the interfering sources. If you go to a site that's good for conventional radio astronomy, this is the Parkes Radio Telescope near Narrabri, Australia, and you take a spectrum, this is what you get. The diagonal thing cutting across here, that is the astronomical background. So you're starting to see it, but you've still got an awful lot of interference here. This is TV in the middle. All right, so what you really need to do is go far, far, far from anything. This is a spectrum from Malura, Australia, which is a sheep ranch in the outback, population 4. And the what? Not counting the sheep, but the sheep aren't fortunately radio transmitters, so they're okay. They don't knock over telescopes either, fortunately. So here, this diagonal part is what we're after. Okay, so that's one challenge. The second is that it turns out that the ionosphere, the top layer of the atmosphere, which consists of ionized gas, is either refractive or even opaque at these frequencies. And what that means is it basically acts like an optical seeing layer. So I know you heard about adaptive optics yesterday. And basically, radio astronomers operating at these frequencies have to use similar techniques to fix their images from the distortion caused by the ionosphere. However, because the scales over which this is operating are slower and bigger, we don't actually shake the antenna around. Instead, we do it all in software. Okay, so this is one area where computing is absolutely essential. You need to do this correction, and it's really hard. The second challenge that you face is that this is not the only astronomical signal at these frequencies. This is the Milky Way. Probably seen this before. Turns out the Milky Way is a very bright source at these wavelengths. In fact, about 10,000 times brighter than the cosmological signal that we're after. And so what you're really trying to do when you make these measurements is pull out a needle from a haystack. And that also requires some very sophisticated computing. So one of the projects has one of the Blue Gene machines from IBM that they're using to make their measurements. And all of them have spent as much money in designing the software as they have in actually building the telescope. It's a very high-end computing challenge. All right, so I'm going to skip some stuff for time. The bottom line is that it turns out that with the instruments we can build today, we can't actually make maps like I showed in this calculation. Instead, what we try to do is measure statistical properties of those maps and how they change with time. And so over here is one of those statistics, and I'm not going to even explain what it is. I just want you to see that it's changing quite dramatically as you go through the different stages of this process. And so we can actually learn a lot by doing the statistical measurements. That's a very different kind of measurement than most astronomers are used to. Instead of focusing very tightly on one little object and observing it for a long time, instead what you want to do is just look at a huge volume of space so that you can gather as many statistics as you can across that space. And that, again, is something that requires a lot of computing, especially for a radio telescope. OK, so I want to end by talking about some of the experiments that are being built to do this. So one thing you can try to do is just measure the average background as a function of frequency, the plot that I was showing you with the shape. And this is an experiment that's trying to do that. It has the awkward name of Experiment to Detect the Global Epoch of Reionization Signal. So they call it EDGES. It's led by Judd Bowman at Arizona State. The antenna is this flat metal plate down here. That's the entire experiment. It's a really small thing. Because they're measuring the signal across the entire sky, this is exactly the right kind of antenna that you want. You want to actually be sensitive to the entire sky. You don't want to point your telescope at anything in particular. So that's a very small kind of two-person operation. Another telescope that has done this is the Giant Meteor Wave Radio Telescope, which is in India. So it looks like a traditional radio telescope. It operates at lower frequencies, though. This was not actually, well, it was sort of built to do the kind of things I'm talking about, but when it was built, they didn't understand how to do it, and so it wasn't built properly for it. Through no fault, I'm not criticizing the people who made it, just they didn't know what kind of thing to build. But people have gone back to this big telescope, and they basically retrofitted it to do the kinds of experiments I'm talking about. And that team, which is led by Whaley Penn in Canada, put the first constraints on this signal a couple of years ago. The University of California experiment, led out of Berkeley by Aaron Parsons, is called the Precision Array to Probe the Epoch of Reionization, or PAPER. If you haven't noticed yet, astronomers are a little nutty about acronyms these days. So this is one of their antennae, although the white part is not the interesting part. That's just basically a shield. If you can see the copper bars going across here, that's actually the antenna. It's just basically a stick, or two sticks that are crossed. And what that does is it's sensitive to the entire sky. What they're going to do with this, though, is actually use 128 of these simple antennae and network them all together in what's called an interferometer that gives you, not only can you see the whole sky at once, but then you can zoom in on particular patches and start to measure these statistics. The philosophy of this experiment is that we're looking for a needle in a haystack. And so to understand whether you found a needle in the end, you need to understand your search process in exquisite detail. And so they're keeping things as simple as they can to make sure they understand the experiment at a very, very deep level and can pick out the needle at the end. So this is basically the exact opposite of the Giant Meteor Wave Radio Telescope. So this is a satellite dish that points, in a particular direction to measure the signal. This looks everywhere at once and then uses the fact that it can see so much to make a measurement. The problem with this approach is that each of these little telescopes is very small. And if you want to see a very faint signal, you need a really big telescope. And so the other two experiments take a hybrid approach, where basically they start off with something very similar to the PAPER antenna, but then they tile a bunch of them together. Okay, in the case of this experiment, 16 of them, and then they use that as an element in their interferometer. And so that gives you 16 times more collecting area. Okay. But it has two consequences. One is that you can't see as much of the sky at once, so you don't have as much volume to measure your statistics. And the second problem is that it makes it a much more complicated experiment, and so it's harder to extract the signal at the end. Okay? So one of these experiments is called the Murchison Wide Field Array. That's in Western Australia. By the way, PAPER is in South Africa. And then this is the last one, LOFAR, the Low Frequency Array, which is in the Netherlands. MWA is really focused on this particular application, and so it's basically cutting as many corners as it can in its design and hoping to get the optimized experiment for this purpose. LOFAR is a general purpose radio telescope. It's 10 times bigger than any of these other ones in both cost and area. But it's not designed for this specific purpose. And so it turns out to be not 10 times better, but just a few times better. For me, as a theoretical astrophysicist, the exciting thing is that there are all these different experiments all taking very different approaches. And they're all going to be starting observations or have observed within the next 6 months. And so we should really, it's kind of a race to see who can be first, except nobody's going to believe whoever's first, so somebody better be second as well. And then we'll figure out what the best approach is, and then that's when you take off toward the future. Very last thing I want to mention is it may be that, especially at lower frequencies, that we simply can't do this from the Earth. The interference in the ionosphere are too hard. And so the best place to make this measurement is actually the far side of the moon. You could put a satellite around the Earth, and that wouldn't help you, because you would then get all of the radio interference from the Earth. But if you go to the far side of the moon actually blocks any signals, any contamination from the Earth. And so you have a very clean observing window over here. So I'm part of a project that would like to send a satellite orbiting the moon and try to measure the sky average signal from over there. And then we can go to really low frequencies and really possibly get the very first signals from the first stars and black holes. This is something that we could build today. We just haven't gotten funded for it yet. Okay, so I'll stop there. Thanks.
We have about 7 minutes for Q&A to make up for the late start and the issue with the mic.
Someone else has started. You did mention the square kilometre array, which has been much in the news lately. As first, it was rumored that South Africa was going to get it, and then apparently a deal was worked out that it's going to get shared between the region where the purchasing array is in Western Australia and also South Africa. So we want to tell us a little bit more about what the role of that can be as a kind of follow-on to the projects you mentioned that are actually going to be taking data now or very soon.
Yeah. So the question is about the square kilometre array, if you didn't hear, and what role it plays in this. So the square kilometre array has been a project that people have contemplated for at least 20 years to build a very, very large radio telescope. And it has had some serious political problems because it has tried to be the radio telescope that will solve every radio problem, and that's impossible. So what they've ended up doing is splitting the telescope into 3 parts, 2 of which they started thinking about building. One would work at low frequencies, including the ones I've described here, and one would work at higher frequencies. It's a little bit hard for me to say what role that's going to play in this area because nobody has figured out what the telescope will look like. And when you're building these complex interferometers, the design that you give the telescope is absolutely crucial to determine what kind of limits it can and observations it can make. So for the kind of applications we're talking about here, what you really want is a telescope that's very compact. It just has a huge collecting area, but doesn't spread over many miles. If you want to observe individual objects in astronomy, you need high angular resolution, and the way you get that is by spreading your telescope very widely. So the balance between those 2 goals is going to determine just how well the square kilometre array can do. Right now, the United States community is actually not thinking about the square kilometre array as something that we want to build right now, because we think that you need to figure out basically which of these many kinds of telescopes is the best strategy to observe. So should you be building something like paper that is not that high collecting area but is a very well understood instrument, or should you be trying to build a hybrid thing like the Murchison Wide Field Array? Until we get data from these 2 kinds of things, we don't feel we're in a position to commit $1 billion to build another instrument. The Europeans somewhat disagree with that. They favor building just a big version of LOFAR because they think they can do that. If you do get a square kilometre array, then you can start to not use statistics but actually make maps. And that will be a huge step forward, undoubtedly. It's just a question of how do we get to that point right now. Yeah, so the antenna here are these basically gold. So if you remember the paper picture, there were those 2 copper pipes, right? So the gold things here are the copper pipes. And it had that white thing on the bottom, that fence-like thing. That's what these poles are right here. It's basically shielding it's pointing the telescope not backwards but forwards. So you're not seeing the moon, you're just seeing the sky. It's a TV antenna in space, really. I mean, it's got to be the simplest $100 million experiment ever contemplated. The cost is not in designing it. That's very easy. The cost is in basically getting it space flight ready and getting it to orbit the moon. Just getting this amount of mass to the moon costs a lot of money. So we have, it's about $150 million. That fits into a small program by NASA standards. So we're going to be proposing it again probably next year when the next cycle comes up. It could. So there is a lot of interest in the human spaceflight program of going to the moon. And so we're pursuing avenues to kind of piggyback on that kind of thing. You can't simply put it on a satellite that's going to study the moon, because those satellites all use the kinds of frequencies we want to observe for their communications. And we need something that's shielded from any other contaminating source. So you wouldn't just put this on another telescope. You could put the satellite, next to another satellite that's being launched out there and share the launch cost. But you wouldn't want to just put it on another satellite.
Can someone just quickly explain the Dark Ages?
OK, so Dark Ages was originally coined to refer to the era that we couldn't see, basically. It originally encompassed the entire era from the CMB, cosmic microwave background, to the sort of teenage galaxies that I described. It's now basically been distinguished, so the Dark Ages refers to before the first sources of light filled the universe, whereas the cosmic dawn is kind of the dawning of those first sources. So this is a little imprecise. We're going to be hoping to go down to just where the first stars form. So it's kind of the old meaning of Dark Ages in this name.
I mean, is there a reason why we can't see why we can see the cosmic microwave background? Like, what's the reason for the space in between?
So the cosmic microwave background photons are actually created back when the universe was hot and dense. Basically, when you have any hot, dense gas, it's going to radiate in what's called a black body. And those are the black body photons from that early time. Once the universe became neutral, so those photons continued evolving, their properties continued evolving with the universe until they decoupled from the normal matter in the universe, the gas in the universe. Once the gas became neutral, then the photons couldn't interact with them anymore because the photons were too low energy. And so from that point, the photons just free stream. They just travel in straight lines to us. And so we can't use those photons as a probe. And then the universe itself is too cold to generate photons of its own, except through the indirect techniques like this spin flip line.